spring, but for obvious reasons, we had to cancel. And rather than wait for an opportunity to do this in person, we decided to go ahead and have this virtual. The Davis Distinguished Lecture has been going on now for about 10 years. We've brought in, I think, some of the real giants of our field, people to name a couple of names, John Kahn and Mildred Dresselhaus, and a number of others, and this year's no exception to that. This is supported by a very generous support from Robert Davis, a former faculty member on our department, who is normally here in attendance, and he may be in attendance, and if this were live, this would be a chance to acknowledge and thank Bob if sitting in the audience. So I'll just take this virtually, a chance to thank Bob for his continued support for this lecture series. And we're very proud of this series and the opportunity to grow this and have very distinguished folks come in and visit with us and present their work. All right, so now I'm going to turn this over to Professor Augustin to introduce this year's Robert Davis Distinguished Lecturer.
All right, well, good morning, everybody that's on East Coast time. Good morning, everyone else from other parts of the world that's joining us. I'm Veronica Augustin. I'm an assistant professor in the department, and it's my great honor to introduce our 2020 Davis Lecturer, Professor Clare Gray, who's the Jeffrey Morehouse Gibson Professor of Chemistry at Cambridge University, as well as a fellow of Pembroke College, Cambridge. Professor Gray's work has truly revolutionized the way that we characterize and understand materials for energy storage and energy conversion devices by introducing the use of solid-state nuclear magnetic resonance and diffraction techniques into our field, particularly in the realm of NMR. And she's received numerous accolades for her research. There's so many to list, including the Research Award from the International Battery Association, the Royal Society Davy Award. And I think one thing that comes to my mind when I think of truly exceptional people in science is where do her graduates go? And I think in your case, Claire, if we look around the major university departments in the US and around the world, the people who have come through your lab are now leading research groups of their own that are very busy advancing and continuing this great work. And I think that shows the tremendous advancements that you've brought to our field. So thank you so much for being our Davis Lecturer, and I look forward to your presentation today.
Well, thank you very much. I was going to say it's been delighted to be here, but it's obviously sad that I couldn't be there. But I'm glad that we could at least have a presentation today, and hopefully we can find a time when it might be possible to actually meet in person. I've now lost my screen. Sorry. Let me just carefully and slowly share my screen. So what I wanted to do today was, since it was a general lecture, to really give you an overview of some of my work and give you some background information. So can you all see that now?
Yep, looks good.
Yes, we can.
Okay, good. So what I wanted to do was to focus really on some of our development of new NMR and other methodology to understand lithium and beyond lithium-ion battery technology. But because it's a general audience talk, I wanted to give you a little bit of a sense of where batteries were, talk a little bit about sustainability issues, where some new research areas are and current directions, and then use that introduction to map that onto some of the work that we're doing, particularly focusing on, for the first sort of 1/3, on development of operando methods, particularly NMR spectroscopy, and I'll try and go through as many of these applications as I can, given the time. And then I'll end a little bit by talking about new materials for fast charging and also some redox flow battery applications. So just to remind everybody that this doesn't need a reminder, why is this important? Really, there are two areas. One is in the whole electrification of transport, and their cheaper and longer lasting batteries are important, but this has to be done with the context of sustainability. And then the sort of the really big challenge that we all have to come up with is, how do we do storage on the grid? And that is one where current batteries are only really suitable for short-term backup and frequency regulation. So I think sort of as scientists, particularly speaking to the PhD students and postdocs in the audience, this is where you all have to step up to the plate and think about new chemistries, new material science, new engineering to really make impact on the grid. And I think it's one of the society's biggest challenge if we're going to get more renewables onto the grid and meet some of the targets for reduction of CO2. And that in itself is a whole political discussion, but we'll leave that to questions. So just to put up the slide that of the battery chemistry that everybody's familiar with, the only point I wanted to make was that this battery, while nominally containing just two materials that are important to get it to work, really involves a lot of engineering and chemistry and material science to get the structures to be able to cycle stably for multiple cycles. And it's really amazing that lithium-ion batteries work as well as they do. But I think that one of the points that is now becoming apparent is that we're really quite close to the theoretical limits of the current technologies. And so if you look at this nice graph produced by George Crabtree and co-workers a few years ago now, they were able to show that the energy density, or in this case, the gravimetric energy density, has increased by about a factor of 3, going from some of the early systems through to the NMCs, that if we really want a step change in energy density, we're going to have to think about new technologies, be it lithium air or lithium sulfur, possibly even magnesium. And at the same time, what you have is this dramatic reduction in cost, some of it due to scale up and engineering, and some of it just to these very large manufacturing activities. But this all comes at a cost, and some of this is safety. And this is the Samsung Galaxy Notebook, where really this was an issue of just trying to get 5% energy density by putting the same amount into a smaller volume. And so one has to really bear the safety aspects of all of the increased energy density into the whole equation. So this is a picture of John Goodenough, of course, with Stan Whittingham and Akira Yoshino, won the Nobel Prize last year. And this is him on the day of the announcement of his Nobel Prize. He was actually at the Royal Society in the UK winning another prize, when this is the glass of port for both events. So, and the point really is that it's pioneering, but there's a lot more work to really make impact, particularly in grid scale applications. So just to give a sense of where we're going, if you talk about the lithium cobalt oxide system, the push in electric vehicles is to move away from the more costly and unsustainable cobalt oxide into the lithium nickel oxides, but that then brings issues in terms of instabilities at high oxidation states. So nickel, when you remove all the lithium, becomes nickel 4+, and nickel 4+ is not very stable with respect to losing oxygen. And so what the field does is to reintroduce the cobalt and then dope with other elements to increase the stability of the system. And that comes with, as you go to more nickel rich, you end up with, you have more capacity, but then your capacity retention, so that's the retention as you cycle the battery, diminishes. And so the field is really trying to think about how do we enable these nickel rich materials, but also to get higher energy density, but at the same time improve capacity retention. And I'll come back to that later on in my talk. And then the other point I think is important, particularly when talking to a material science department, is it's not just the chemistry, it's also the morphologies. And if you look at the lithium cobalt oxides of this world, they're made of these so-called single crystals. And when people say single crystal in this field, they really mean just large micron-sized particles. But if you look at an NMC type system, then they're made of these large secondary particles, where the primary particles are maybe only 200 to 500 nanometers. And so that results in very different mechanisms for fracture and failure. And so people such as Jeff Dahn have really pioneered the development of more single crystal based materials in the nickel space to improve energy density. So then this has to be done in the context of sustainability. And I just wanted to mention the fact that the amount of cobalt that is projected to be used as these gigafactories are coming online is phenomenal, and is comparable with the amount of cobalt that's being produced in the Congo at this point. And of course, the Congo production has its own ethical issues associated with it. And so that's been the reason that these car manufacturers are moving away from the high cobalt systems, or one of the reasons. But now you're now requiring all this nickel, and so nickel then isn't in itself a finite element either, and so that brings in resource issues there. And then at the same time you have the lithium, and lithium, there is a lot of lithium in this world. A lot of it's found in Argentina and Bolivia and Chile in the so-called lithium triangle area, but it has sustainable issues in itself. And so this is the Atacama Desert, where they pump the lithium brines out and then they're put into these evaporation ponds. This is an evaporation pond in Bolivia. And as a result of all this additional pumping out of the brines, this area, particularly in the Atacama, is a bit of a high desert area, and that's having an impact in the local populace, and also the populace of things like the flamingos that rely on these the brines and the algae in the brines. And so all of these things have sustainability implications. And so very much the whole recycling and second use becomes important. And again, I'm happy to take more questions on that. So then one has to sort of say, what about moving beyond lithium? And this is just sort of pointing out the obvious, that if you can't do lithium, what about sodium? Sodium has a potential that's only about 0.3 volts from the lithium potential, and a lot of the chemistry is very similar. Obviously, the higher natural abundance means it's much cheaper, and there are also things that are less obvious, like you can replace the copper current collectors that are in lithium technology on the anode by aluminium or aluminum, depending where you do the chemistry, and that's because sodium doesn't react with the aluminum, unlike the lithium. And so that's another reason for cost reduction. And it's been surprisingly easier than people thought, and it's almost a drop-in technology. But one of the challenges is that you can't use graphite, because you can't intercalate sodium into graphite. And so the challenge is to come up with these so-called hard carbons to do the work. And then you might be more ambitious and move towards magnesium batteries, but it doesn't take much sort of thinking as a solid state chemist or material science to think about the fact that magnesium is a 2+ ion. So if it's going to move through the cathode, then the activation barriers are going to be much higher. And so that's going to make it much more sluggish. But the motivation is that because it's a 2+ cation, you have more space inside a material, for example, to hold the magnesium. And so in principle, you could get higher capacities. But not only the problem of mobility, one of the biggest challenges is actually to be able to strip and plate magnesium, because it's a 2+ cation. And so the best sort of materials to date are these Chevreul phases, so these molybdenum sulfides done by Dorn Auerbach, and those work because the sulfur is smushy and you get reasonably low activation barriers for transport. But the electrolyte is challenging, and this is just one piece of work from our studies. So this is work with myself and my colleague Dominic Wright, who made magnesium PF6. So in the lithium space, LiPF6 is the major salt that's used, and before our work, no one had made a pure form of the magnesium PF6. And so this is now in a magnesium PF, is the salt in the electrolyte, and this is our electrochemistry with the Chevreul phase. And you can see the challenge here, that the stripping and plating over potentials means you have such a large over potential between charge and discharge, which is not practical. But the other reason why people like magnesium is that you don't form these dendrites under reasonable rates. So this is an example of, instead of the dendritic structures you get in lithium that I'll show you more of later, you get these globules, and that's another attraction for magnesium. But it's an area of work in my group, but it's one where there are tremendous challenges to get that to be commercial. And so what about the sort of paradigm shifting technologies? If you really want to go be cheaper, you should get rid of your transition metals, and maybe you can use sulfur and make a lithium sulfur battery, and you get very high energy densities because both lithium and sulfur are light, and of course sulfur is cheap. But you've got problems associated with the fact that the sulfur goes from S0 to S2- via polysulfides, and these polysulfides dissolve into the electrolyte, and act as redox shuttles. And so that's the challenge in that field. Meanwhile, in lithium air, which is another field we work on, lithium reacts with oxygen to form lithium peroxide, but it does that via a superoxide ion, which then attacks the electrolyte. And so even though lithium air is the only chemistry really where you have the same gravimetric energy density of gasoline, both theoretical and practical, it's got lots of challenges. But it's one where, as a research academic, I feel that we need to keep on working on, because if we're going to make significant changes in this field, we have to be doing the science now to enable these new technologies. And this is just work of ours, and also some earlier work by Peter Bruce in the UK, showing that if you use these redox mediators, you can go in and you can take these large lithium, in this case peroxide crystals, and on charge you can then oxidize them with a reduced form of tempo, or in discharge you can react the oxygen with the DBBQ, which is a quinone molecule, and control basically the sizes of the and where you actually do the chemistry. And so, there's steady progress. And so I think it's very much watch this space. And then finally, just in the sort of overview, the ultimate in safety is to forget the liquid electrolyte and make it all solid. And this is a spark plasma synthesis battery made by Michael Dolle and his group. The cathode is here. This is the solid electrolyte. This is the anode. And you can just see the challenges of getting the lithium through these highly things with multiple grain boundaries, and each of these materials, when you're pulling the lithiums in and out, will expand and contract, and so the potential problems for fracture and failure are significant, but an important area to work on. So I would say that if you really want to sort of think outside the box, you need to think about ways of really scaling, and I think to do that using the concepts of redox flow, where you can decouple the oxidized, or in this case, the reduced and the oxidized forms here in liquids. And when you want to do the electrochemistry, you flow them into the cell, and then you can generate the electricity or the power, depending what you need or what the major requirement is. But you kind of decouple the idea that the battery has, where the energy density is this fixed box, and that fixed box contains all you need. And this is in principle scalable for grid scale applications, and the problem at the moment is just too expensive. So the other thing that I would like to at least argue is that if you're really going to get more sustainable chemistry and get cheaper chemistries, you really got to understand battery degradation and to think about ways of increasing lifetime. And also, if you're a chemist or a material scientist and you're making new materials, you really want to then understand how they work, so that you can understand how to put them together at the electrode level all the way through to the cell level. So you kind of worry about the structures, you worry about how the lithium ions get in, how the electrons get in, and how they're all wired up together. And so my work has been very much in the last 10 years now, is to think about in situ metrologies, but particularly using NMR spectroscopy, which is sort of my area of expertise. And it's not as simple as just taking a battery and putting it inside an NMR spectrometer and getting signals. And the primary reason for that is that a battery has a can, and this can is made out of metal, and NMR spectroscopy is done with a radio frequency field, and that has to penetrate the can. And so in the first instance, you've got to think about bespoke designs that look as close as the real thing, but still allow you to do NMR. And in addition to that, one then can start about thinking about the things about why one would want to do that. And I would argue that it's particularly important to do these operando studies to try and look at sort of metastable products and look at structures that if you took the whole battery apart, they wouldn't survive. And so we've originally starting off in Stony Brook, where I was a faculty member for a number of years. My former student at the time, Barish Key, really got the project going. And then Ollie Pescher in Cambridge worked with a German company to try and build probes and automate the whole system, where we can basically take our NMR probe and we connect it up to a battery cycler on one side, and on the other side a spectrometer, and we control things all remotely. And of course, controlling things remotely is what one wants to do these days. But I just wanted to sort of walk you through from an NMR perspective, and I realize that this is a technique that may not be used in all material science departments, what some of the challenges are. And I think the thing that one needs to appreciate the most is that batteries contain metals, they contain liquids, they contain paramagnetic materials. And the result of that is that there are a lot of interactions which are useful from an NMR perspective because they tell you something about what's going on, but they also make it more difficult to measure and interpret the signal. And just to sort of illustrate, around 0 ppm is where you see diamagnetic things. So they could be the electrolyte, the liquids in the electrolyte, or what's known as the SEI, which is this passivating layer that forms on the anode at low potentials. But then you have very large shifts to see the signals of lithium metal or sodium metal in a sodium battery. And those are affected by the so-called night shift, which is a signature of the density of states in the metal. So you kind of, these are good things, but in practice, it makes the NMR detection more difficult because you've got to be able to sweep these very large ranges. And then you've got the sort of very practical things that if you put your battery inside a coil, and this is a battery that just emphasized the fact that these batteries are often not safe, and this is a silicon battery that met an unfortunate fate and caught fire. But this also shows you that you've got these leads coming in, and that's where the electrochemistry comes in, and they all act as antennae. And so then you have to worry about getting rid of spurious noise from the frequency, for example, in the wall or the lights. And so all of that requires optimization. So relatively straightforward, but it's taken some time. So these are our cell designs. This is the first design where we used a plastic bag, and those plastic bag designs are what are often found in sort of old laptop batteries, where you use the same technology that people use to laminate smoked salmon, or also known as a coffee bag battery, because you're using the same plastic covered by aluminum foil in coffee bags anyhow, and we use that to laminate our batteries so we can get the RF through. These are better designs where we get better pressure on the cell, and then we can do things like automatically tune the probe, and that allows us to hop between different nuclei. So let me just give you a few examples. This is an overview of the sodium space. I just wanted to start by showing you what we've done in that area to remind you that in the sodium chemistry, you can't use graphite, and what you use is this hard carbon. And so by just doing sodium NMR of this hard carbon, we can unpick the different processes that go on. And then you look at the electrochemistry, and you can relate the electrochemistry to the local environment as seen by the sodium. And what you're seeing in this sloping process is the lithium that goes in, and it's in more diamagnetic environments near defects. And then in this flat process, close to sodium plating, the sodium actually fills the pores or the holes within the hard carbon, and it forms sodium metal. And then you see this dramatic shift of the peak towards the position of where sodium metal is. And so what we're doing when we're looking at this cell is we're using what's known as a half cell. So on one side of we have the electrode is the hard carbon, and then instead of the cathode, we put in sodium metal just to simplify things. And so just by doing one relatively simple experiment, you can then watch the sodium moves and become more metallic. And you can correlate that to, for example, the internal porosity inside these hard carbons, and you can corroborate that with, for example, Sachs measurements. And this is another example of another potential potential sodium anode material, and that's tin. And these are very attractive because you can react sodium with tin to get very, very high capacities. And so you can just about, I'm going to have to put my glasses on this one, you can just about see how high the capacity is. You're getting 1,000 milliamperes per gram out of tin, whereas in carbons, you would get no more than about 300 milliamperes per gram. And so if you can, it's of use to work out what's going on, so we can optimize this chemistry. And what we're doing here is, again, using the sodium NMR signatures to unpick and solve all the intermetallics that are formed when sodium reacts with tin. And then we can combine this with a technique, paired distribution function analysis, which is simply a total scattering method where you take a normal Bragg diffraction pattern, except you measure everything, so the diffuse and the Bragg scattering, and then you do a Fourier transform and you bring it into real space, and each of those peaks tells you something about the pairwise correlations in the sample. And it's a very simple measure in this case to look at, for example, the crystallinity of the material. And so you start with tin, and tin is crystalline. You start to then react with the sodium, and you can see now by this point, you only have very short range correlations as the material becomes amorphous. And so what we do is combine the NMR information with the PDF measurements, and also we do theory at the same time to sort of predict what phases we might see. And then we were able to solve the whole phase diagram for this chemistry. And so just to sort of give you another flavor of where else we can use these type of methodologies for, this is actually a supercapacitor. And so supercapacitors are again carbons, but now instead of these hard carbons here, where you've got a very dense carbon, what you do is you activate your carbon to give you a lot of internal porosity. And so these carbons have internal porosities of maybe even 1600 meters squared per gram. And so they're almost sort of graphene sheets held apart to let the ions in. And then when you charge them, you form, you store charge by forming a double layer or intercalation of ions inside the pores. And what we were able to do was now use, in this case, fluorine NMR to look at the BF4 minus, to actually look at the ions going inside the pores and to quantify how many ions went in and what the charging mechanism therefore was in these different hard types of activated carbons. And then you can also see that the peaks shift backwards and forwards as the voltage goes positive and then negative. And what you're watching is the change of the density of states on the carbons, and that then has an effect on the field felt by the NMR nucleus. And so we can be both quantitative, we can also say something about the electronic structures of the carbons, which is quite interesting. So let me now just tell you a few more longer stories about where we're using our in situ NMR. And the first one we did was to really use the NMR to look at silicon. And silicon is the material that people are excited by because in principle, if you could use the silicon instead of a graphite, you could get 10 times the gravimetric capacity, or also 10 times the volumetric capacity. And you know, sometimes you care about volumetric capacities, sometimes gravimetrics, depending on whether, for example, it's a drone or an aeroplane, or this is a laptop or a car where you might be more concerned about the volumetric energy density. So what we did was to look at this a number of years ago, but I want to sort of illustrate what the problem of this material is, that it's so reactive when you form these lithium silicides. It reacts with the electrolyte to form this passivating layer called the SEI, or the solid electrolyte interface, and you gradually lose energy density. And so this is work in 2016 that we did, but what we did first, almost 7 years previously, was to really understand what was going on in terms of the structure. And what we do when you have a reaction of lithium and silicon, you want to sort of understand what sort of phases will be formed. And so we go into the phase diagram, we find all the model compounds, we go and make them, and we learn what the lithium NMR spectrum of these different compounds would be, and try and relate the shifts that we see to the local structure. And so the Li12 Si7 and the Li7 Si3 compound contain little clusters. And so this is one type of cluster where you get a silicon-silicon bond surrounded by lithium, and that gives you these peaks at about 18 to 20 ppm. And then when you have isolated silicon, so in this final compound, the Li15Si4, you get shifts at lower frequencies. And so with that learning, we can then make what we call do ex situ studies, where we make lots of different batteries, we pull them apart, and we do NMR. And you can see in this study that when you first lithiate, you form these sort of cluster things, and then when you continue to react, you form the isolated. So this is the sort of ex situ study. And then we moved into the in situ study. We did it originally in this JAX paper, but this is another series of work where we did it on silicon nanowires, where you can see beautifully that you form these clusters. But what's sort of surprising is you see this peak at negative ppm, which is this so-called Li15 plus X phase, where you've added a little bit of extra lithium to this Li15 phase, and you can see you've dramatically shifted the frequency. And what that was actually telling us was, and this is again just showing the same thing now as a contour plot, so here's the Li15 phase. When we we discharged all the way to low voltages, we stopped and we watched, the open circuit value increased and this signal disappeared. And what was happening was that this phase was so reactive, it was reacting with the electrolyte. In itself, it was being oxidized to this phase. And so that meant that when you were looking at things ex situ, as shown in this study here, you couldn't actually capture that phase, but only by doing it in situ could you actually see this phase. And what we were seeing back in 2009 was the sort of first evidence of this problem that I show you here, that the silicon is so highly reactive, it continues to eat the electrolyte up and just form this horrible mess of decomposition products that gradually eat lithium from the cell and result in a reduction of capacity. And so the challenge now is to add additives to mitigate this reaction. But the real problem is the silicon expands and contracts, and as it does, it exposes fresh surfaces and the reaction continues. And so that's why silicon still can't be cycled for more than 200 or 300 cycles, unless there's a strategy such as limiting how much you cycle, or maybe adding graphene, or looking at various composites. And again, happy to talk more about that later. I wanted to show you this one example, partly because I was talking to a material science department, where it's a nice illustration of how you can use these methods. So this is a results now for the spinel. I'm now on the cathode side, and this is a material where you've got manganese in the octahedral sites, and these are the lithiums that can go in and out. And you can oxidize this material at 4 volts, and there are 2 processes, one at about 4, one at 4.2 volts, and you can do NMR on it. These are now paramagnetic, and so the lithium interacts with the manganese ions and basically gives you broad lines. And we normally use this technique, magic angle spinning, to get rid of it, but in a static battery for in situ, we can't do that. So you get these broad features. This is lithium metal. Again, we're running the lithium manganese oxide in a half cell. I'll talk about the lithium metal signal a bit more. But if you now look, instead of at the movie, just look at the stack plot, you can see here's the signal, it goes away, and that's not too surprising because you pulled all the lithium out of it. But what's not was not surprising to us is that at 0.5, you actually see an increase in the intensity. And NMR, and so if you think about that for a while, NMR is meant to be quantitative. If you do your experiment properly, your signal should be proportional to how much is going on, how much is there rather. So there has to be something else going on. And that, of course, is how you do the measurement. And the way we do the measurement, without going into sort of gory NMR details, is a so-called spinner echo experiment, where you apply a pulse, you wait a time, you apply another pulse, and you detect. And the point of this second pulse is to refocus the signals. But if you have a system where the lithium ions are moving, and they move in this period and they move in this period, the signal you had here will not be the same signal as you have here, and you lose signal. And we measure that via so-called spin-spin relaxation, or T2 prime, and that's a measure of motion in the microsecond regime. And so what you see is, so this is now a measurement of the T2 during cycling. So we start off with a value of about 100 milliseconds, but then you pull a little bit of lithium out of the structure, and the T2s drop dramatically. And that's very simply that you have a structure, it's stuffed full of lithium, you pull a few lithiums out, you have vacancies, and the mobility goes up. And so as the T2 drops, and then when you hit this 0.5 composition, you form an ordered phase in the material where you can order lithium filled, empty, and the lithium slow down. And so the T2s increase slightly, and that then means that you see more signal, and that's why you get this apparent increase. And so just by doing these relatively straightforward experiments, you can say something about the dynamics of the material on the fly. And then you can start to ask questions like, can we say something about the phase transitions? And so this is now looking at the same material as a function going from room temperature to 70 degrees. So going from lithium 1 to lithium 0.5 to lithium 0. In the first region, as a function of temperature, the T2 varies all over the place, and then which is sort of consistent of a solid solution behavior. In the second region, you have a essentially almost constant value of T2, where the value at 0.5 stays almost the same at lithium 1, where there isn't actually any lithium left. But that's indicative then of a two-phase reaction. And so in the same way that you can think about variables in a phase rule, you can then determine that if this parameter is a continual variant, then that sets the number of phases in the system, and so it becomes a solid solution. While it's a constant, it's a two-phase reaction. And then what's interesting is where we saw this cation ordering at low temperatures, you can see that when you heat up at higher temperatures, you no longer get this cation ordering. And so just by doing these experiments without knowing all the details of how and the interactions that drive these things, you can say something about the phase transformations that occur in these materials. So I'll just tell you one more story now about safety. So this is the picture of the poor Dreamliner that was grounded a number of years ago. And at least one thought behind what was going on was that there were dendrites that were forming and that were catching fire. And the reason you don't use a lithium metal anode, you use graphite instead, is that instead of forming nice smooth deposits on lithium metal, you can form these dendritic structures. And then if they short circuit, then you have problems and fires. And even graphite, and I'll show you this later, you can, if you charge this too fast, you still form lithium dendrites. And so what we recognized was that there was another problem with NMR, and I mentioned this when I talked about exciting your signal in the AAA battery, is that you have a problem of skin depth in a metal. So a metal, there's only a limited depth that the radio frequency can penetrate. And for lithium 7 that we use to excite, that we use to detect our NMR, you can only detect about 15 microns at the frequency we're using. And so that means you can see a dendrite, but you can't detect the full volume of the lithium metal anode. And so what we did then was to use that as a way to track dendrites. And this just shows you a nice illustration of this, where we have a so-called symmetric cell. We've got lithium on one side, and you're going backwards and forwards, plating and stripping, plating and stripping. And as the current increases, you can start to see the growth of the dendrite. And so there's the peak increasing. And you're simply measuring the effective surface area of the system, because you can't detect the full lithium anode strip. And at the same time, you can watch what's going on at 0 ppm, and that's the electrolyte, and this is also the passivating layer. And you can see that once you form a dendrite, that dendrites then get covered in this passivating layer, and so that signal goes up. And at the same time, you can see that the sodium dendrites have just been going. So sodium dendrite is even more problematic. So then you want to think about, how do dendrites grow? What drives them? So in order to do that, this was a number of years ago, we paired up with Alexei Gershaw and his group at NYU to do MRI. And here you're seeing a magnetic resonance image of lithium metal with a liquid. And these are the lithium metal in black, and in red is the electrolyte. And what we're doing is we're flowing current. So the lithium ions go in this direction, and the counter anions, in this case, the PF6 I was talking about, they flow in this direction. The lithiums deposit, the PF6 can't, and so you build up a concentration gradient. Okay, so now watch the lithium metal. So what you first of all see is the lithium growing up in these mossy structures, but when the concentration gradient hits 0, you get a space charge or an electric field that drags the lithium metal out, and you form dendrites. And you can see this more clearly in the so-called chemical shift imaging. So this is again the lithium mossy structure that grows, and then when the electrolyte drops, you get dendritic. So we can go back now, and we can go into the sort of classical studies of metal deposition and try and work out why and how this happens. And there's a study by Chevaziel and others who looked at this in the context of the so-called Sand's time. And the Sand's time is when that concentration of the anions drops to 0, and you get this sort of space charge mechanism. And we can look at the electrolyte, experimentally determined electrolyte depletion, and the start of the dendrite growth, and everything works out well, and our NMR tracks it. But at low currents, in principle, you should be able to get to a regime that's shown here, where you don't actually get a 0 concentration of electrolytes, but you still start to see dendrites. And the reason for that, sadly, because if this didn't happen, it would mean you could just back off in the current and you still have no problem, is this passivating layer that forms. And because this passivating layer is cracking and is not very homogeneous, as the dendrite grows or the film grows, you can get regions where you get high electric fields, and you can get dendritic structures. And so the challenge now is to think about what that passivating layer looks like to control it. And so that's what we've been focusing on in the last few years. And this is an example where we're trying to understand how this works by looking at the normal electrolyte, and this is the additive fluoroethylene carbonate. And you can see that if you add different additives, you get very different morphologies of dendrites. So this is the standard electrolyte, and this is the FEC additive. And the reason that this grows in more nodules and less dendritic structures is got to do with the rate of the lithium transport through this SEI, this passivating layer. And that's something we can then quantify by doing isotope exchange experiments, where we can, for example, look at lithium-6 metal in a lithium-7 electrolyte and actually quantify that effect. So the sort of take-home message from that is, if you make an SCI with very better lithium transport, then you can move towards these less dendritic structures and in principle, hopefully get more stable cycling. I want to show you something else, which is really cool. And this is some new methods that we've been, I wouldn't say pioneering, for the reasons I'll explain in a second. We're using a technique called dynamic nuclear polarization, or DNP, where we transfer magnetization from the electron spins. And this technique was first invented back in the 50s and 60s. And it was predicted by Overhauser that you could actually use lithium metal DNP. So you could use the unpaired electrons in lithium as a source of polarization. And Charlie Slichter and his group 10 years later actually showed this experimentally. And this was sort of largely forgotten about until we looked at this last year. And we showed that if you basically blasted the lithiums with microwave power, you could then result in a massive, well, not a massive, but a significant enhancement of the lithium metal signal by, in this example, sort of 8 times. We've had up to 10 and 20 times if we increase the power. So that was essentially the experiment that was done by Charlie Slichter 50 years ago. But what we did then was, which I think is where it's exciting, is we then transferred directly from the lithium spins of the metal to this passivating layer to see what the protons were doing and what the fluorines were doing. And we were actually able to look at this lithium metal SCI interface. So not the interphase, but actually that interface to understand that chemistry. So that's something that we're really trying to push at the moment. Sadly, I talked about solid state batteries as being maybe a solution to the safety issues in terms of getting rid of the electrolytes, but this is just showing you an example of doing now lithium magnetic resonance imaging of LSZO, so lithium lanthanum zirconate pellets, that one of the most stable materials against lithium metal. But you can see that even lithium metal is able to force its way around these large LSZO particles. So this is a cross section of the SEM of a short circuit pellet. You can see the lithium metal, and you can see by the EDAX that it's where everything else isn't. And then by NMR or MRI, you can see the lithium that's going through the pellet. But you can use these methods now to understand and correlate the electrochemistry with the progression of the dendrites through into these pellets without having to do cross sections and be destructive. And so you can take a thick pellet where you've got a large overpotential, and then once the sort of dendrites or moss starts growing into it, the overpotential decreases because it's a shorter distance that the lithium has to travel. Then you get these sort of signatures of short circuits. And then when you start to see the whole lithium signal going from one side, then you really got failure of the cell and short circuits. So I just want to end with a very, I'll try and be quick, on a study coming out of the EV, electric vehicle space. So the UK has a new institution which is trying to sort of bring together the UK activities in batteries to work with the car manufacturers to understand, well, not to understand, but to do improve battery technology. And I lead the activity on battery degradation or extending battery life. And we've been developing methods to look at NMC 811. So this is this cathode material with nickel, manganese, and cobalt. 80% nickel, 10% cobalt, and 10% manganese. And just to sort of show you some examples of what we do, this is the cathode material lithium nickel oxide that has a really complicated series of phase diagrams, phases it forms as you remove lithium from the structure, and you can follow that with diffraction. But if you look at 811, it's much more simple. And so this is work we did a while ago using the Ampex cell at the APS, where you can track the layer spacing, for example, with this 1, 0, 0 through reflection, and get the cell parameters. And there's no change in phases, so you have a continuous solid solution. But what's interesting is this massive decrease in the C parameter, which is the spacing between the layers. So let's reflect on that a bit more. So this is the C parameter collapse. So here's the layer structure. And so you can break that down into the spacings in the lithium layers where the lithium ions move and the metal layers. And when you do that, you can see that you carry on to about 200 milliamperes per gram, and then you get this collapse at about x equals 0.75. And so let's think about this in terms of the implications for mobility. This is work of Gerd Seder and Kisuk Kang and myself on some of this a number of years ago, where we thought about how lithium ions move in the materials. And basically, as the layers collapse, you get a short repulsion between the layers, lithiums in the layers. So in order to hop, you've got to go octahedral site, tetrahedral site, octahedral site. And in the tetrahedral site, there's a short contact with the metal below. And so as the layer collapses and the charge of the metal goes up, the activation barrier goes up. And so you could see that these C parameter collapses would be bad for mobility. So in order to test that hypothesis, we did NMR, of course. This is now magic angle spinning, and I just wanted to show you what a magic angle spinning spectrum looks like. So you've got lithium in the initial compound here, and this lithium sees all of these paramagnetic ions, and the lithium and the nickels and the manganese are all arranged almost randomly in the structure. So you see this very broad spectrum. You start pulling lithium out of the structure and it sharpens up. And it's not intuitive why it should sharpen up, particularly when you get to the end, you actually get a broader spectrum again. And it's got these two distinct peaks here. And over years, we've worked out the whole language of how to explain these NMR spectra. And basically, you could look at this lithium and you can say what is in the first coordination shell and what is in the second coordination shell, and what shifts would you get from the interaction of a nickel or a manganese with the lithium. And at the top of charge, all of the nickel is nickel 4+. Nickel 4+ is diamagnetic, so it doesn't give you this shift called the hyperfine shift, but the manganese is the one that gives you the shift, and it has a large shift of about 250 ppm when you have this so-called 90-degree interaction. And so this resonance is due to one manganese, and this is due to two manganese in the local coordination shell. So we can get the sort of exquisite level of information of local structure. So that's nice, but we haven't explained this. And what's going on here is that this is the signature of lithium mobility. And you can probe that by doing variable temperature NMR. So as you go up in temperature, the lithium ions move more. And so in this case, if you get sharpening, that's a clear signature of mobility. And so in this regime at 0.5, the lithium's already moving quite fast, even at close to room temperature. And so my postdoc Katerina did a nice study where she modeled the whole thing and was able to fit the spectrum. And by doing that, she was able to quantify the hopping frequency as a function of where state of charge. And basically beyond about 0.25, the lithium start to move, but at 0.75, they stop moving. And then you can do similar electrochemistry experiments, or not similar ones, to confirm that. And so if you go back to this model we had then of the structure, you can correlate this drop in the lithium transport at 0.75, and that's where the lithium layer collapses. And so you can then see that that will pull them together, and that will result in reduced lithium capacity. And so the sort of implications from a battery perspective is you should really cycle your material in the regime where the lithium ions move fast, and that will be more favorable in terms of less heating effects and less resistance from transport. I just wanted to sort of bring the whole thing together by showing you a picture of now Katerina's work where she makes full cells. So instead of cycling the 811 against lithium, we now put graphite into the mixture. And so this is the spectrum of the NMC, and it's this broad signal. You pull the lithium out and it disappears. And at the same time, you can see now this signature here coming in and out. And that's the lithium going into the graphite. So you can watch the various staging compounds, and this is the signal of lithium in the stage 2 and the stage 1. And so you can track that all together in operanda cell. But this is now the fun part, when she then started doing things at different temperatures. And so if you go down to 10 degrees and then down to 0 degrees, you can start to see the signal of lithium metal. So this little line here is the signal at 200 ppm where lithium metal happens. And so when you get to low temperatures, the activation barrier of getting the lithium in, coupled with the transport in the electrolyte is so high that you start plating. And so we can then start looking at the plating phenomena in these materials. Okay, I'm going to sort of rush through by saying we've also done experiments where we cycle things in long durations. And so we look at what happens to the diffraction after multiple cycles. So this is after 348 cycles. So we have a cell and we periodically look at it in the beam time at a sort of number determined by the synchrotron scientists, not us. And you can start to see this broadening of the 003 peak that tells you something about the spacing. And you can then model what's going on, and you can see that you no longer see a single phase, but you see phases or components that no longer fully cycle, which we call the fatigue phase. And we can then analyze this over multiple cycles. And as the cycle number goes up, the fatigue fraction goes up. And so by the time you cycle it for about 915 times, pretty much all of the phase is fatigued and isn't able to cycle over the full range. And what we think is going on there is quite interesting. So we've looked at single crystals. So I talked about these single crystals as being the sort of next stage, and you get exactly the same problem in these materials. So it's not a problem associated with particle cracking and fracturing. It's to do with something else. It's not a problem with lithium mobility. So we do the same lithium mobility experiments, and the lithium ions are still mobile in these materials. But instead, what we noticed was that the fatigue phase always failed at the same state of charge of about 75%. And that's at a particular C/A ratio. And that C/A ratio, so I talked about this idea of the C parameter going up and then collapsing, and it's at where it starts to collapse at about 0.75. And what's interesting about that is that correlates with the formation of a rock salt on these materials. So I introduced at the beginning this idea of nickel 4+ not being very stable. It loses oxygen and it forms a nickel oxide rock salt, NiO, on the top. And by doing some very careful electron microscopy, and this is in collaboration with Leila Mahdi from Liverpool and her group, we were able to look at the registry between the rock salt phase and the layered phase and see that the registry of them is exactly perfect when this material is fully expanded. So if you look at the 75% state of charge, then the spacings between the rock salt and the layered phases are almost exactly the same. And so what we think is going on is a curious mechanism where the surface is pinning the structure, and so it prevents that collapse of the layer, and the further removal of the lithium would then require this layer to collapse. And so there's a lot of issues of interfacial strain that we need to work out, and we need to think about how these surface phenomena propagate into the bulk. But we don't believe it's a simple impedance thing. We believe there's a surface pinning effect. And I should probably sort of draw my talk to an end by just sort of summarizing some of what I've been talking about before I go on too long, by just saying I hope I've shown you that a combination of NMR and MRI are really able to show you a lot of information about structure and of crystalline phases, amorphous phases, and poorly amorphous structures. We've been able to track dendrites. We've been able to quantify lithium mobility, and we've been able to extend this to a whole variety of different materials. And the thing I didn't talk about much was my high-rate lithium niobates, but I can talk about that another time. And if I was actually in Davis, I might have been able to give some more informal talks. But so I meant if I was in NC State rather giving the Davis lecture, I might have been able to talk about a few things more informally. But I think I'd rather stop and take questions from you now. But before I do, I just wanted to acknowledge my research group, who are truly spectacular. And this is us last year when we could actually go on group retreats up in the mountains, reasonably close by. I talked about some of the people doing the in situ work. Rangeet was the one who pushed the lithium dendrite work back in back in Stony Brook, the Supercap people, and Chow and Katerina and Phil were really the people who worked on the NMC. And thank you very much for listening to me.